Okay, previously we had talked about the surface conditions on Venus in the previous lecture, the incredibly high temperatures that exist there, and the very high pressure, 90 atmosphere, 90 times the atmospheric pressure of Earth. Now, that atmosphere turns out to be mostly carbon dioxide and nitrogen. Now, it's 96.5% CO2. Earth's atmosphere has almost no CO2 in it. We have nitrogen and oxygen. The oxygen is produced by biologic activity. Well, interestingly enough, if you were to take Venus's atmosphere and take away all of that CO2, what's left is going to be the nitrogen, and you're going to end up with an atmosphere that's really not that much thicker than Earth's atmosphere. And so, again, mostly made of nitrogen, just like Earth's atmosphere is mostly made of nitrogen. So the big difference between the two turns out to be primarily all that CO2. That turns out to be the defining factor between Earth's atmosphere and Venus's atmosphere, is the CO2. Well, the other thing about the atmosphere is, what I just said was the atmospheric conditions at the surface. So this graphic right here shows that red line across the middle shows you what's happening as you go into higher elevation. So on the left is your altitude. On the right, it tells you what pressure is at that altitude. And then it tells you up here the temperature. So by the time you get up to the cloud layers here, the lower cloud layer, which is like 50 kilometers up, then the temperature, the pressure is about 1 atmosphere, so it's almost the same as Earth. The temperature is only slightly less than 100 degrees Celsius. So it's just slightly under the boiling point of water. But by the time you get up to the upper layers of the clouds up here, so the upper cloud layer up here, then that's about 60 kilometers up. So 60 kilometers up, we're talking like 40 miles or something. Then what happens is that the pressure is a bit lower here, but the temperature is about 0 degrees Celsius, about the freezing point of water. The middle layer here, about 55 kilometers up, so about 30-something miles above the atmosphere, the temperature is really about 30 degrees Celsius. That's about room temperature on Earth. And the pressure there is, well, it's lower than atmospheric pressure, but not massively lower than atmospheric pressure. This is like the pressure up in the Rocky Mountains somewhere. So this is actually clearly a livable temperature, were it not for the fact that the clouds are made of really nasty stuff. The clouds are made of sulfuric acid is the dominant composition, but there's worse things there. There's phosphoric acid, there's hydrosulfuric acid, there's hydrofluoric acid, there's fluorosulfuric acid. There's a variety of different sort of things up there. So the atmosphere is nothing. The clouds are not very nice. These are very, very toxic sort of things. The clouds are very high up. Now, the thing is that at lower levels in the atmosphere, it's too hot to have, and too high pressure for those droplets to be stable. So they're not going to be stable at the lower elevations. And so at too high of altitudes, it's too cold and too thin of an atmosphere. And so the cloud layers are right there in the middle. Now, these are very high up. The cloud layers between 50 and 75 kilometers, this is so high that on Earth, that's above the stratosphere. That's like in the mesosphere on Earth. And so these are very, very high altitudes above the ground. Again, indicative of just how dense the atmosphere is for Venus. In those clouds on Venus, you're going to get sulfuric acid droplets that come together to make rain. That's just like on Earth, water. Now, on Earth, the rain cycle is that up in the upper atmosphere, water vapor condenses out and condenses either as a solid, it'd be ice like cirrus clouds, or if they get big enough, it rain. You can get sleet or snow, or it condenses out as liquid and you get rain. Okay, or droplets. It may be clouds. When the droplets get big enough, the gravity makes them fall, and you get rain. And so this is what happens on Earth. The rain falls to the surface, collects, evaporates, goes back into the atmosphere, repeats the process. But it's always water. It's going to be solid water. That's going to be ice or snow, or something. It's going to be liquid water. That's going to be rain, or it's going to be, or the droplets of the clouds, or it's going to be water vapor. But it's always H2O. It's always the same chemical. On Venus, the sulfuric acid droplets will form in the clouds, and as they get heavy enough, they will fall, due to gravity, just like on Earth with the raindrops. But remember, at lower altitudes, then it's not stable as a droplet. And so what happens is it starts to evaporate, and then the high temperature actually dissociates it. It pulls it apart into hydrogen and sulfur dioxide. That's an endothermic reaction, so it actually takes heat from the atmosphere. Now, those gases then rise through the atmosphere back up to the upper parts of the clouds, where they come back together to make sulfuric acid, H2SO4. So that is exothermic, meaning that it releases energy back into the atmosphere. And so this turns out to be a way that Venus has of getting heat from below the clouds to above the clouds. Remember, on Earth, on a cloudy night, the heat goes up, bounces off the clouds. Same thing on Venus. The heat from the surface has trouble getting past the clouds. Just ignore the whole CO2 and greenhouse gas. The clouds themselves are a massive deterrent to heat radiating into space. And so this process of raining sulfuric acid, dissociating as gases, coming back, making sulfuric acid, that helps get the heat from here up to there, where it's released outwards. So this is one way that Venus uses to get the heat out. Well, the other thing that happens in all of this is, on Earth, we know that the sunlight heats the ground, and that causes hot air to rise. As it rises, that causes circulation. That gives you the weather patterns. On Venus, instead, the weather patterns are in the clouds. The sunlight causes circulation in the cloud layer, and because the atmosphere is kind of thick, it drags the atmosphere above and below, and so that causes the circulation patterns here. So we have a driven cell. The driven cell is up in the clouds, and that's the driving cell that's driving everything, and then that drags everything else. So that you have vortices in the northern region, but basically all the main circulation is happening in the cloud layer. That means that what's happening at the lower levels is not predominantly caused by the sun, but secondary. That means that you have less wind at the surface. Now, that's actually a good thing, because remember, the atmosphere is 90 times thicker than Earth's atmosphere. So that means that a 1 mile per hour wind at the surface, that'd be like nothing on Earth. That's barely a gentle breeze. And that would be like a hurricane force wind, because it would have the same force as a 90 mile per hour wind. Strong hurricane force at that. So that's one reason that you don't any kind of wind at all on Venus would completely scour the surface. And so now the fact that it's a driven cell down there is less active, and so the good news is there's very little wind on Venus. That means very little wind erosion. No water erosion, no wind erosion. So the rocks on Venus are pretty much, when you get a volcanic rock, it stays that way. The circulation is so efficient that it distributes the heat very efficiently around the planet. Now, Earth has some circulation here that distributes heat in the atmosphere. We know that happens. For example, in the wintertime, we get cold fronts, so cold air, moves south. Warm air sometimes moves north. So we do have circulation that moves hot and cold air around. On Venus, on the other hand, this is so efficient that practically the entire planet is the same temperature. Most planets are hotter in the day, cooler at night. They're warmer at the equator than they are at the polar regions. Venus, pretty much planet-wide, day, night, equator, poles, almost all the same temperature. That's driven by that mid-level atmospheric convection cell, called a Hadley convection cell. And that cell in the clouds is driving all the atmospheric circulation. And it's actually so efficient at moving the heat around that wherever you go on Venus, it's pretty much the same temperature, no matter where and when. And so there's almost no variation. Now, really studying the atmosphere, we want to be there and study it up close. A couple of the Venera spacecraft studied the atmosphere, but really the biggest studies came from the American Pioneer Venus. So in 1978, Pioneer Venus was launched to Venus, and so it had two parts: an orbiter that orbited around the planet with a radar altimeter, so that as it was flying over the clouds, it would just measure how high it was, and that would let you know where there's mountains and continents and anything like that. So it would let you build sort of a very sort of a gross sort of profile map of Venus. The other one here, though, had an interesting sort of thing. It had 4 detachable subprobes that dropped in the atmosphere, and as they fell through the atmosphere, they recorded temperature, pressure, composition, and so forth. And so until they got so far down, they got crushed by the pressure or burnt out by the heat. One of them, amazingly, made it all the way to the surface and then bounced off the surface and continued transmitting for a few minutes before it died. The biggest of these probes, of those 4 probes, actually had a mass spectrometer in it. This is a device that measures the masses of atoms. And so it was put together and launched as a project, a PhD project, by a student at University of Texas at Dallas. And the idea was it would fall through the atmosphere and measure the exact chemistry of the atmosphere. It would measure the exact atoms that made up the atmosphere, not just the atomic species, not just the particular element, but also which isotope it was. And so this would give a very detailed profile of Venus's atmosphere from high altitude all the way down until the probe was crushed near the surface. And so at least that was the idea. Now what actually happened was, as it fell through the atmosphere, that probe eventually encountered the clouds. And the mass spectrometer had this tiny little narrow tube that was letting gases into the device, and that tube got plugged by a sulfuric acid droplet. And so for the rest of the way down to the surface, as it was falling, rather than measuring the atmosphere, it measured that one sulfuric acid droplet. And so we got incredible measurements of that sulfuric acid droplet, but his PhD was on the atmospheric profile of the planet. So he ended up not getting his PhD, and having spent several years researching Venus and developing a model here and building the probe, having it launched, and then it not working, he had to start all over for another several years to work on another project to get his PhD. And so that's one of the hazards of graduate education for a PhD, particularly in the sciences. Your experiment doesn't work, and you don't get a degree, and you have to start all over again. So, but we did get data on that one drop. Okay, that just was not helpful for him. But this was the Pioneer Venus, and so it did measure the upper part of the atmosphere, with these other probes, to much higher precision. So this gave us our best understanding of the atmosphere at that time. Now, since then, we've had other spacecraft that have been to Venus. They've not actually entered the atmosphere, but they have studied from space.